In this video, I want to talk about the ideal gas law. Now, this is something that we jumped into right off the bat when we were dealing with stoichiometry, just because so many different questions involve the ideal gas law. So let's just kind of revisit that and pick it apart a little bit and just review how this pertains to stoichiometry and whatnot. So ideal gas law, if you remember, is PV equals nRT. Remember that my pressure here must be in atmospheres, ATM. My volume must be in liters. N stands for moles. Now, I never, ever, ever can plug in a coefficient in right there. I have to do some stoichiometry, do some stitches in order to figure out those moles there if it's not given to me. The R is your gas constant, which is 0.0821. And my temperature is T, which must be in Kelvin. Now, when we're talking about the ideal gas law, the reason why it's named this is what we were talking about, the kinetic molecular theory. We make all these assumptions and whatnot. Well, we make even more assumptions in order to work with the ideal gas law. So gases, we say, behave ideally under certain conditions. And that means behaving ideally is just making this math a lot cleaner than what it actually is. So when we say gases behave ideally, there's two pieces of criteria that must be met in order to behave that way. So at low pressures, gases behave ideally, and at high temperatures, gases behave ideally as well. So both of these things must be met in order to be able to use PV equals nRT. So this is something we haven't discussed yet. So I've seen some multiple choice questions, and the reason why I keep reinforcing multiple choice is this is mostly where you're going to see gas laws on the real AP exam. There's lots of multiple choice questions that pertain to this. So when we're working with this, we want low pressures, high temperatures. And if I go away from that, like if I have high pressures, low temperatures or whatnot, we say that our gas deviates from ideal. And so I have a little diagram here to show you that. So you have a red line here, a purple line that's spiking up, and then a green line that's kind of in between. Temperatures are accordingly. So 873 Kelvin, this is the highest temperature at red. The green is the middle temperature, and the purple is the lower temperature that you have there. So notice on my axes, we have pressure here and then PV over nRT right there. Now, ideally, PV over nRT will equal to 1. That's your ideal gas component right there. So you see ideal gas there. Now, what we look for here is you notice how if I have lower pressures, so my pressures are pretty low in this area, you deviate less, or you deviate from ideal rather than when you have higher pressures. So what this is showing is that as you're increasing your pressure, your gases are starting to deviate from ideal behavior. Also, notice that high temperatures, so even though that this gas here that is in the red line is going to a higher temperature, a higher pressure, because it has the highest temperature, it also deviates less from ideal. So I've seen some multiple choice questions where you have to kind of interpret this graph, and that's all that is pertaining to. Low pressures, high temperatures, you have a more ideal gas there. So when we're working with PV equals nRT, most of the time we can solve for a number of different things. Most of the time you're solving for moles, or you're solving for volume, or you're solving for pressure here. But you can also solve for temperature. And again, this R value is 0.0821. The reason why is because the units there are liters, atmospheres, over mole Kelvin, which corresponds with all the units that we have in PV equals nRT. A couple of other things that I want to show you here is if we have STP, and this is something we talked about in stoichiometry. So at STP, if you remember, STP means 0 degrees Celsius and 1 ATM. So if I look at this and I solve for volume here, so volume would be nRT that's an N right there, over P. So if I plug in this specifically, so 0 degrees Celsius would be 273 Kelvin here. R would be R's value, and P would be 1. If I plugged all of those things in and solved for it, and I plugged in 1 mole for N, guess what number I'll get for V? Well, that number is 22.4. So when we were working with stoichiometry, we said, oh, well, we can just set up a stitch to convert liters to moles or moles to liters and use that number 22.4. Where that number was coming from was this RT over P, but it's very specific. It's at STP. So I wanted to show you guys that again to just kind of reinforce the idea. Another thing that we can do with Pivnert is we can derive to figure out the molar mass formula. And so this is the molar mass kitty cat equation. And if you remember, we dealt with this in stoichiometry as well. So hopefully some of this is just a bit of a review for you. So the molar mass equation, all it is derived from Pivnert. So molar mass equals D, which stands for density, R, which is your gas constant R again, T, which is temperature, and P over pressure. So anytime I have an unknown molar mass, I can use this equation to solve for that. And where this applied in our stoichiometry unit is when we were trying to figure out the molecular formula of these things that we were finding empirical formulas for. So that's where you see it most often. So what I have here is just a couple of examples dealing with the stoichiometry and the molar mass kitty cat equation, and just so we can kind of reinforce and review that idea. So if we read this first example, it says you have quicklime, which is calcium oxide, is produced by thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP, this is a huge term right there, produced from the decomposition of 152 grams of calcium carbonate. So it gives us the balanced reaction. And basically what we want to do is convert 152 grams to volume of CO2. So because we're getting from one thing to something else in the reaction, we're going to have to end up doing a mole-to-mole ratio. Now, where you will see STP most of the time is in multiple choice questions because it's easy to work with 22.4 mathematically. So how I'm going to figure out this answer is I'm going to start with the 152 grams of calcium carbonate, so CaCO3. And the very first thing I have to do is convert to moles. So I'm going to use the molar mass of calcium carbonate, which is 100 grams. And that's equal to a mole of calcium carbonate. The next thing that I'm going to have to do is convert from calcium carbonate to CO2. So my relationship between them is a 1-to-1 relationship. So I have 1 mole of calcium carbonate for every 1 mole of CO2. Now what I've done is I've converted all the way, if I cross out my units appropriately, I've converted to where if I did the math here, I would be getting moles of CO2. And what I want is volume. Now, because it says STP, I don't have to stick the moles into Pivnert. Instead, I can just use 22.4 liters is equal to 1 mole. Now, if this wasn't at STP, what I would do is I would have to first of all get more information, but stick that information into Pivnert to solve for my volume. So it makes it a little bit easier because we are given STP. So my next part of the stitch is going to be 1 mole, 22.4 liters of CO2 is equal to 1 mole of CO2. And then we work through that math. So if I work this mathematically, I get something around 34.1 liters of CO2. And this is just reviewing the stoichiometry, we're reworking this and how it pertains to the gas laws. So that's the first question on the example that I have here. Now for the second example that I have. So we have a sample of methane. Methane is CH4. is having a volume. So we have a volume, we have a temperature, we have a pressure for methane. So CH4 there. And we have it mixed with a sample of oxygen gas, and the oxygen has a volume, a temperature, and a pressure as well. So this is for oxygen. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.5 atm and a temperature of 125 degrees Celsius. All right, so this question is a little bit of a doozy. So what we have given is information about methane, and we have enough information to where we can find moles of methane. We also are given information about our second reactant, which is oxygen. And we have also enough information to where we can figure out the moles of oxygen. So back to your stoichiometry days, which you guys love oh so dearly. We're going to have to first figure out the moles of CH4 and O2. And because we have information about both of those reactants, we have to figure out which one is my limiting reactant. Then, once I figure out my limiting reactant, I then can figure out how much CO2 will be produced, moles, and then, because we're not at STP, we're going to have to figure out what our volume is by sticking those moles into PivNert. So, work with me here. Let me give me some more space so I can work this problem with you guys. All right, here we go. So, first thing, I'm going to use PivNert for methane and PivNert for oxygen, and that's going to give me moles of each. So, PV equals nRT. I'm going to pause this and kind of write all this out so I can save some time. So give me just a second. All right, so when I take this and I work PivNert, I plugged in all of my information for methane. So 1.6 atm, 2.8 liters, N is what we're solving for. My R value, 298 is this 25 plus 273. When I solve for the N here, I end up getting 0.189 moles of methane. Now I'm going to do the same thing for O2. So I work with PivNert. I get 1.25, 35, N, 0.0821, 304, which is 31 plus 273. So I'm just getting that information for my problem. My N that I find for that one is 1.75 moles. Now what I have to do is look at this CH4, which I know is 0.189, and I have to look at the O2, which is 1.75 moles, and I have to figure out which one of these is my limiting reactant. Well, I can't just compare these two numbers because this is a 1-to-2 relationship. So I would say this divided by 1 is 0.189, and 1.75 divided by 2 is like 0.8 something. So if I compare those two numbers, that still tells me that CH4 here is my limiting reactant. And what that means is that I am going to use all of my limiting reactant. So minus 0.189, so I have 0 left over. Now it's just all about stoichiometric relationships. Because there is a 1-to-1 mole-to-mole ratio of CH4 to CO2, then that means that 0.189 moles is going to be produced for CO2. All right, that's all about the mole-to-mole ratio right here. This is where a lot of you guys get mixed up. Now that I know how many moles of CO2 has been produced, all I have to do now to figure out the volume is to plug that into PivNert using all of CO2's information. So I'm going to go there. I'm going to say PV equals nRT. The pressure for CO2 is 2.5. It says 2.5 right there. The volume is what we're solving for. Oops. That's supposed to be nRT. The N is what we just found, so that's the 0.189. R is 0.0821. 0.0821, the R constant, and the temperature is 125 degrees Celsius, which if we add 273 to that, that is 398. So now all we have to do is work with Pivner, solve for that, and you get a volume of 2.47 liters, and that's our final answer. So again, the reason why we had to do all this, working with Pivner and all of that, is because we were not given STP. We also were given information about both of my reactants, so I had to figure out which was my limiting reactant first. And then you can solve for your unknown variable in Pivner, giving all the other stuff. All right, so let's scroll down to the next example problem and work that together. So this next example problem is dealing with the molar mass kitty cat equation. And the reason why we know that is because it says calculate the molar mass and it gives us the density. So we're going to say molar mass equals dRT over P. And all we have to do is plug in our density, which is 1.5. Oh, I'm sorry, that's not 1.5. It's 1.95 grams per liter, so 1.95. Our R value is 0.0821. My temperature is 273 plus the 27, so that would be 300 Kelvin. And divide by P, which is the 1.5 atmospheres. So now it's just a matter of plugging all that stuff in my calculator. So I get molar mass is equal to 32.0 grams per mole. And that is my molar mass. So pretty straightforward. So I hope these practice problems were a little bit of a good review for you guys, especially that second one. And our next video will be on combined gas law.